Direct, serious. When an application scales to millions of concurrent operations, treating data structures like infinite magic buckets eventually shreds system stability. The Java collection framework is often introduced as an abstraction, where commands like add and put are frictionless, constant-time operations that stretch endlessly to accommodate data. Beneath that abstraction lies a strict mechanical reality. These collections are governed by finite, contiguous primitive memory blocks anchored to physical hardware. Pushing data into collections without anticipating their physical limits forces the Java virtual machine to execute silent compensation routines in the background to prevent a total fault. Senior engineering validation requires navigating these algorithmic structures, bits distributions, and sizing mechanics to maintain performance under load. Software abstraction simplifies development, but executing it incurs a tangible hardware tax in CPU cycles and memory fragmentation. Take the standard ArrayList. It is a wrapper over a rigid, contiguous memory block called elementData, which allocates exactly 10 empty slots by default when first initialized. The mechanical problem arrives on the 11th insertion. The JVM cannot simply append a new memory block to the end of the existing array, because heap memory is rarely contiguous for separate allocations. To determine the necessary space, the JVM applies a bitwise right-shift formula. It takes the oldCapacity of 10 and shifts the bits to the right by one position to yield 5, calculating a new target size of 15. Shifting bits to the right is a highly optimized method for dividing by 2. This math forces the system to instantiate an entirely separate 15-block array in a different sector of the heap, exactly a 1.5 times capacity expansion. To bridge the two, the JVM executes a native memory copy. It routes a command through System.arraycopy to physically duplicate the original elements into the new blocks. This hidden native copy temporarily freezes the thread. What was an O of 1 amortized append degrades into a linear latency spike as every single byte is read and rewritten. Amortized constant time is merely a statistical average that masks severe, unpredictable execution penalties down at the physical hardware level. Dynamic arrays carry a secondary penalty, triggered by mid-list alterations, like inserting or removing an element at a specific index. This sequence shows a targeted insertion. Because the layout must remain contiguous, forcing a new item into the middle requires the system to physically slide all downstream array elements left or right by one position. To mitigate this, architecture guidelines suggest pre-sizing the container upon instantiation whenever the target capacity of a dataset is known. Declaring the capacity upfront entirely bypasses these intermediate allocation loops and eliminates the resulting garbage collection footprint. Anticipating dataset mass is the only way to shield the CPU from memory fragmentation and unnecessary allocation cycles. While ArrayList manages contiguous blocks, HashMap uses a different strategy, routing keys to specific array indices using hardware-level bitwise logic. It operates under a rigid constraint. The backing array of buckets must always scale to a strict power of 2, such as 16, 32, or 64. Standard index routing relies on mathematical modulo division, taking the hash of a key and dividing it by the capacity to find the remainder. That division is computationally expensive. This comparison shows why the power of 2 constraint is enforced. It allows the JVM to replace division with a bitwise AND mask. Subtracting 1 from any power of 2 creates a bit mask of trailing 1s. When applied against a hash code, it instantly clips the value, guaranteeing the index stays within the array boundaries. By forcing the memory to scale in powers of 2, the system subverts software-level math for raw hardware speed. This masking system is vulnerable to poor hash code distributions, which cluster too many keys into the same bucket. To prevent these collisions, the map passes the value through a spreading function. It XORs the top 16 bits of the hash directly onto the lower 16 bits. This forces variance in the top half of the integer to alter the indexing logic, which reduces the frequency of bucket conflicts even when the backing array is small. When the stored elements reach 75% of the current capacity, the map hits its load factor threshold and must double in size. Because the capacity doubles, the bit mask changes. Every single element currently stored must be rehashed and remapped to a new position to align with the new mask. This total structural realignment temporarily increases the latency of the collection as the JVM rebuilds the index map. If extreme collisions bypass the spreading function, elements stack up in a linear linked list inside a single bucket. Java 8 introduced a structural safeguard. When a bucket reaches 8 elements, it's scheduled for conversion. If table capacity is under 64, the JVM triggers a standard resize, splitting the elements. If 64 or greater, the linear nodes convert into a balanced Ned-Black tree. This mutation transforms the lookup from an O of n linear scan into an O of log n logarithmic path. If removals drop the density back to 6, it converts back into a standard list. This dynamic mutation is the JVM's final defense against the degradation of lookup performance. These mechanics operate predictably in a single-thread environment. But in multi-threaded systems, simultaneous reads and writes can expose data corruption risks. Standard containers like ArrayList and HashMap return fail-fast iterators to handle this risk. These rely on an internal primitive counter named modCount that increments on every structural modification call. Upon instantiation, the iterator takes a snapshot of this counter, storing it as the expected modCount. On every step, the iterator verifies that these numbers match. If another thread alters the structure, modCount increments, the comparison fails, and the system instantly throws a concurrent modification exception. Fail-fast iterators are primitive tripwires. They are designed to stop execution rather than allow the iteration of potentially corrupted data structures. Instead, concurrent collections rely on fail-safe iterators, which are designed to completely eliminate these exceptions through strict physical structural isolation. In a copy-on-write array list, the iterator captures an immutable pointer to the array snapshot at the exact moment of creation. If another thread adds an element, the JVM spins an entirely separate array copy on the heap. The iterator continues scanning the original static array, ensuring it never reflects live modifications during that pass. Concurrent HashMap takes a different approach, using weakly consistent iterators that step through volatile bucket nodes directly for lazy state reflection without locking. Developing high-performance software requires moving past the illusion of frictionless methods. At the senior architect level, systems must be designed around the tangible realities of memory contiguity, bitwise masking, and concurrent invariant isolation.